Let's take some time to go over the solutions to those practice problems from 11.1 and 11.2. So let's find the slope of the tangent line to the curve f of x equals 5 times the natural log of 2x minus 3 at x equals 2. So here we're just looking for the slope of the tangent line. Remember, the slope of the tangent line is measured by the derivative, so the first thing we'll have to do is find our derivative. This right here, this 5 is a coefficient that's just going to multiply in the end. And then we'll take the derivative of the natural log of 2x minus 3 by doing our little inside derivative over inside function, or I prime over I. And so we take the 5 times the derivative of the inside function, which is 2, over the inside function 2x minus 3. We can distribute that 5 to the 2 up top, and that gives us the derivative. Now remember, the derivative is kind of like a formula to find the slope of the tangent line at any point. We want it specifically when x equals 2, so the slope we're looking for is the derivative evaluated at 2. So that's going to be 10 over 2 times 2 minus 3. 2 times 2 minus 3 gives me 1, so this gives me a slope of 10. Let's find the equation of the tangent line to the curve g of x equals 3 e to the 2x at x equals 0. So now I'm not looking just for the slope of the tangent line, I'm looking for the actual equation of the tangent line. In order to write the equation of any line, you need two things, a slope and a point. We just talked about how we'll find the slope using the derivative. Now we don't have the point, we only have half a point, so we're going to need to find the y value that goes with this point. What is the ordered pair on this graph when x equals 0? So the y value we're looking for is the function evaluated at 0. So we'll plug in x equals 0. 2 times 0 is 0. Anything to the 0 power is 1, and 3 times 1 is 3. So the point we're at is 0, 3. So now that we have the point, we'll go and find the slope, and we're going to need the derivative for that. So to find our derivative, this 3 is a coefficient, and then we'll do p prime e to the p. So the derivative of the power is 2 e to the 2x here. That 3 times 2 is 6, and there's my derivative. And again, just as we had just said, the derivative kind of is like a formula that helps you find the slope of the tangent line at any point. We want it at x equals 0, so the slope we're looking for is the derivative evaluated at 0, which gives us 6. So now we have a slope of 6 at the point 0, 3. We can find our y equals mx plus b. Plug in mx and y. So we'll plug in 3 for y, 0 for x, 6 for m, and solve for b. This whole term goes away, and you can see that your b is equal to 3. Probably got that from right here, considering this is the y-intercept when x is 0, right there. So we could have gotten b from that. But here's the work in case you needed to see it. Put it all together, and our tangent line is y equals 6x plus 3. All right, let's differentiate. So let's differentiate the natural log of x to the 4th minus 5x squared plus 7e to the 2x minus 4. So to take the derivative of the natural log, it's the derivative of this inside function divided by this inside function. So we'll take the derivative, that'll be 4x cubed minus 10x plus 7 times the derivative of the power, which is 2 times e to the power 2x, minus the derivative of 4 is 0. So we get 4x cubed minus 10x plus that 7 times 2 gives me 14 e to the 2x over that entire inside function. If we wanted to find the derivative of g of x equals 4e to the 2x cubed minus the natural log of 2. Remember that 4 is a coefficient, and then we're going to use our little p prime e to the p for this. So we'll take the derivative of this power out front, e to this power. So the derivative of this power will be 6x squared minus, this will be I prime over I, or 2 over 2x. Now notice these 2's are going to cancel, so I'm going to be left with 1 over x here. I'll distribute the 4 to the 6 and the 4 to the 1 over x, and I get 24x squared minus 4 over x times e to that 2x cubed minus the natural log of 2x. Let's find the derivative of s of t equals the natural log of t to the 7th. Now, what you might be doing right now as you're practicing this is taking the derivative of t to the 7th divided by t to the 7th. And you're welcome to do that, just make sure you reduce and you'll get the same answer. But we have these properties of logarithms that are supposed to make our lives a little bit easier. What we're taking the natural log of is being raised to a power. I can actually bring that power out front. So this function is 7 times the natural log of t. This is something pretty easy to take the derivative of of, that's just 1 over t, and this is a coefficient, so the derivative is 7 times 1 over t, or 7 over t. Now, if you had taken 7t to the 6th over t to the 7th and reduced it, you would end up here anyway. But it's just trying to explain to you again, and we'll see this in a little bit, why you want to try to expand your derivative, your logarithm first, and then take the derivative. Now take a look at this one, e to the x plus 3, all being raised to the 4th power. What we have here is a case of your power chain rule. We have a function of x being raised to a power. So this is that ni to the n minus 1 times I prime thing we had talked about. So we're going to bring this power down, leave the inside function alone completely, take 1 away from the power, and then we'll multiply by the derivative of the inside function. So this is my I to the n minus 1 times I prime. So bring the 4 down, leave the inside function alone, take 1 away for the new exponent, and then multiply it to the derivative of the inside function, which is just going to be e to the x. Or when we pretty that up, we'll have 4 e to the x times e to the x plus 3 all to the 3rd. Don't forget about that power chain rule. Here we have 12x to the 4th times e to the x cubed minus 7x. We're trying to take the derivative. We have 12x to the 4th times e to the x cubed minus 7. X times x, variable times variable, we're going to have to use our product rule. Derivative of the first, which will be 48x cubed, times the second, plus the first, 12x to the 4th, times the derivative of the second, which will be the derivative of this power, 3x squared minus 7, times e to this power. I'm going to go ahead and distribute the 12 to x to the 4th to everybody in there. And then I'm going to go ahead and distribute this e to everybody in there. And now I'm going to pull out the greatest common factor. Everybody's divisible by 12. Everybody is divisible by x cubed. And everybody has that e to the x cubed minus 7x. So I'll pull out that 12x cubed, e to the x cubed minus 7x, and I'm left with 4 plus 3x cubed minus 7x. And there's my derivative. P equals the natural log of 2x over 3x squared. Notice what I have here, the natural log of 2x minus 1 over 3x squared, variable over variable. I'm going to have to use my quotient rule. That's going to be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So the derivative of the top, derivative of the inside over the inside, 2 over 2x minus 1, times the bottom, 3x squared, minus the top, natural log of 2x minus 1, times the derivative of the bottom, 6x, all over the bottom, 3x squared, squared. I'm going to go ahead and distribute this 3x squared up here. I'll bring this 6 out front, and then 3x squared times 3x squared is going to give me 9x to the 4th. Now notice this has a 6x and this has a 6x, so I can pull that 6x out, and I'm left with x over 2x minus 1 minus the natural log of 2x minus 1. One of these x's, this x is going to cancel with one of these x's, and that 6 over 9 will reduce for a nice final answer of 2 times x over 2x minus 1 minus the natural log of 2x minus 1 all over 3x cubed. G of x equals the natural log of 3x minus 4 over 7 minus 2x all being raised to the 3rd power. Now, for this one, if you wanted to do the derivative of the inside function over the inside function, you could. But if you're going to take the derivative of this right here, you've got power chain rule, and inside a power chain rule, you have variable over variable, you have quotient rule. So you would have to apply the power chain rule and the quotient rule. That's not going to be very fun. So that's what I was talking about earlier. A lot of times, if it's possible, you're going to want to expand your logarithm first. What you're taking the logarithm of is all being raised to a power. You can bring that power out front. You're taking the natural log of two things being divided. It'll be the natural log of the numerator minus the natural log of the denominator, distributing that 3 to both. And so now I just got rid of this, bringing this 3 out, got rid of the power chain rule. Breaking this up into two logarithms being subtracted, got rid of the quotient rule. And so now I can very easily take the derivative 3 times I prime over I minus 3 times I prime over I. So the derivative of this inside function is 3 over that 3x minus 4. And the derivative of this inside function is negative 2 over that 7 minus 2x. And so now I can distribute the 3 and distribute the negative 3 to get a nice final answer of my derivative, 9 over 3x minus 4 plus 6 over 7 minus 2x. Okay, now let's find the second derivative of the natural log of x cubed minus 2. In order to find the second derivative, we need the first derivative. The first derivative will be the derivative of this inside function over the inside function. So it's going to be 3x squared over x cubed minus 2. What do you notice? Variable over variable. So in order to solve this, I'll have to find the second derivative. I will have to use my quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So we get the derivative of the top times the bottom minus the bottom times the top times the derivative of the bottom all over the bottom squared. Distribute this 6x and multiply these two together. Notice that 6x to the fourth minus 9x to the fourth are like terms, and we get a final answer of negative 3x to the fourth minus 12x all over x cubed minus 2 quantity squared. Find d2y over dx2 for 4e to the 9x squared minus 7. What does d2y over dx2 mean? It means take the derivative of y twice with respect to x both times. In other words, find the second derivative. To find the second derivative, we need the first. That's going to be 4p prime e to the p. So it's going to be 4 times the derivative of the power 18x times e to that power 9x squared minus 7. Distribute that 4 and you get 72x times e to the 9x squared minus 7. Now to find the second derivative, I'm going to have variable times variable. That's right, I'm going to have to use that product rule. Derivative of the first times the second plus the first times the derivative of the second. Derivative of the first is just 72 times the second plus the first times p prime e to the p again here. Distribute these two together. And now you can see that they have a common factor. And so we pull out the greatest common factor. They're both divisible by 72. They both have an e to the 9x squared minus 7. And when I pull that out, I'm left with 1 plus 18x squared. So there's my second derivative. All right, another example. The cost for x units of a certain commodity can be found by c of x equals the natural log of 20x minus 1500. Find the marginal cost for the production of 100 units and interpret it with a sentence. All right, marginal cost. That measures how quickly the cost is changing at any given moment. In other words, the instantaneous rate of change of cost. In other words, the derivative of the cost function. So the marginal cost is the derivative of the cost function, I prime over I. And so the derivative now is 20 over 20x minus 1500. And I want the marginal cost for the production of 100 units. So now into the derivative, I'm going to plug 100. And when I do that, I get 20 over 500 or 0.04. So what does that mean? That means that your cost is going to increase by about 4 cents when you make the 101st unit, or it'll cost about 4 cents to produce that 101st unit. All right, so I hope that these practice problems helped you. Of course, feel free to reach out to me anytime with any questions, and I will see you next time.